Code puzzles are an increasingly popular way to introduce programming to children. Code puzzles typically present users with a goal for which they must correctly assemble code blocks in order to achieve. Learners are usually given a set of code puzzles that build upon each other, traditionally in fixed one-size-fits-all sets of tasks. However, personalized education has shown promise in other domains. An adaptive code puzzle system could theoretically present learners with puzzles that are suited to fit their ever-changing level of expertise. In this work, we present steps towards an adaptive learning system which recommends code puzzles to novice programmers in order to control their cognitive load to improve learning. Cognitive load theory suggests that cognitive load should be managed to optimize learning. It states that people experience some level of load or mental effort to complete any task. Extraneous load is the mental effort required to deal with trivial details introduced by instructional materials, while intrinsic load depends on the expertise of the individual and the complexity of the task itself. For example, when a child counts spare change, they may go through every tedious step, picking up each coin, translating it to its cent value, and adding it to a counting sum. An adult, on the other hand, might quickly count how many of each coin there are and easily calculate how much change there is. Code puzzles inherently have low extraneous load by avoiding syntax errors. In the looking glass puzzle interface, learners see an animation in the top left corner and are told to recreate it using the scrambled code blocks in the left-hand panel, A. Users drag the blocks into their program, B, and can test and change their code until it matches the correct animation or they give up. In a previous study, our lab has shown that we can predict what level of cognitive load a learner is likely to experience on a future code puzzle based on their interactions in previous code puzzles. We propose an adaptive learning system that uses user performance to recommend puzzles likely to introduce the optimal cognitive load for learning, allowing the user to progress through a code puzzle system at their own pace. The optimal target cognitive load for learning code puzzles is not known, so we frame this experiment as a dosing trial where we hope to discover this value. Our system recommends puzzles that are predicted to cause medium cognitive load. We believe this to be a promising policy, sparing users from puzzles that are either too difficult or too easy. We created 4 different pathways, or puzzle sets, each building upon the previous. 68 middle school-age children were given several weeks to complete all pathways at home. At the end of each puzzle, users were prompted to rate how difficult the puzzle was on a 9-point Likert scale, from extremely easy to extremely difficult. The participants were divided into 2 groups. The static pathway group received puzzles arranged in the order of what we believe to be the easiest to most challenging, and the adaptive pathway group was dynamically given puzzles based on predicted cognitive load. We found that both groups had similar completion rates, but adaptive pathway users generally experienced higher cognitive load than static users. It turns out that this was not great, as we found that higher cognitive load is a significant predictor that a user will quit. The adaptive users experience fewer puzzles in either extreme. The left skew here indicates that the majority of the puzzles were rated as more or less easy rather than difficult. Since our system recommended medium cognitive load puzzles, the adaptive system learners generally were given harder puzzles. We then took the average mental effort for each user for the first pathway and compared across the users who eventually finish versus those who eventually quit. We found that even slightly elevated cognitive load predicted user dropout. Based on these findings, we recommend a target cognitive load of very easy for another trial, preventing them from dropout risk as well as keeping them slightly challenged. We also explored our experimental data to discover other signs of success and struggle. We first calculated features to capture user behavior, which we observed in a previous pilot study. We conduct PCA on these 40 features by 2,000 puzzles, qualitatively define the components, and then compare each component across the finisher and quitter groups mentioned earlier in order to understand their relationship with successful learning experiences. At a high level, the components are duration, understanding, brute force, editing to information gathering ratio, small picture iteration, confusion, and finally, knowledge seeking, where users go between phases of editing and phases of gathering information. This behavior is significantly higher in the group of users who go on to finish all puzzles and may be a sign of active thinking and learning. Thank you so much for listening today. If you have any questions, please reach out to us. We would really love to hear from you. Thank you so much.